So hey guys, welcome back to another lecture on this machine learning course. So first of all, a happy new year to everyone who are working hard. Maybe this year brings you all your dreams come true. So today we're going to discuss something known as matrices. So as I promised that after completing the every topic, I'm going to give the Python lectures. I'm going to give the Python lectures, their usage in the Python language also. So I just posted the video, so please see it, like you have a hands-on experience like how the vectors are used in Python and etc. So after that we're going to cover something known as the matrices. So what do you mean by matrices and how these are used in machine learning? So as I said, like the data in the computers is not stored in like a alphabetical order. It just stored in a numerical order. It just stored in a numerical order. So to communicate with that numerical order, we just use these vectors and matrices etc. to just communicate with the those kind of things. So what do you mean by the matrices? Like it's just a rectangle or a table of numbers are arranged in rows and columns. So it's just a rectangle or a table of numbers that are arranged in rows and columns. That are arranged in rows and columns. So there are n number of rows and m number of columns. So if we have a matrices like this, if we have a matrices like this, there are n number of rows and m number of columns. So this is rows. This is rows. We call this is rows, and we have a vertical line over there, and this we call as a columns. So they are arranged in a form of a rectangle array. So this like a rectangle array. So there is a difference between the vector and a matrices. Like the vector has a n into 1, like the only one column, only one row. Okay, so the vector has only one row, but the matrices has n number of rows and m number of columns. That's the only difference with these two like a vector and a matrices. So we denote like vectors in a, so we denote vectors in small, and we're having a vector over there, but we denote the matrices in a capital letters. Yes. So in numpy the index starts from the 0. So like here in the matrices, like in our numerical mathematics understanding, we just start from the 1, 2 and 3. But if we when we use in a Python programming, we have a library called numpy, and we're going to discuss in our further lectures. Don't worry, just it starts from the 0. So why it starts from the 0 and etc. I'm going to cover in a few further lectures. Okay. So after that we have a operations on the matrices. After that we have operations on the matrices. So the first operation is like a scalar matrix product. So what is the scalar matrix products? It's just simple as I said, like in a vector thing. It just we simply multiply with the scalar. So here we do element wise multiplication. So here we do element wise multiplication with the each element in a matrix, with the each element in the matrix. Like as example, if the scalar is 3 and the matrix have a 1 2 3 4 1 2, and the matrix has 1 2 3 4, and just we simply multiply these two. We simply multiply with the scalar and with the element wise, and the resulting matrix is called as our scalar matrix product. I hope you understand. And this is a 2 into 2 matrix. So, and I have given another example also, like we have a scalar 5 and we have a matrix out there, and then we simply multiply, we do element wise multiplication, and we will get the output. So you can try out your own examples, like having, we can change, like we can use also in a 3 by 3, just try out your own, or if you didn't get, just comment down below and I'll do it again. So So after completing the scalar matrix product, so we're going to discuss something known as matrix addition. It's just simple as I said in a vector, like adding these two, but we have a similar kind of thing. We have a similar kind of thing, but just a different. Like we simply do element wise addition in a matrix. It just with the other matrix. Like we do the element wise addition with matrix with another matrix, with matrix with the another matrix. That's it, bro. Like for example, we have a matrix and we have a B matrix, and we just do element wise addition, element wise variation, and then we just simply 1 plus 3 and 2 plus 4 and 3 plus 5 and 4 plus 6, and we simply add these, and we will get our output matrix, and that is called as a matrix addition. It's just as simple as I discussed in the vectors. It's just as simple as a vector, so you don't have to be worried about this addition. It's just a basic thing. Like it just do element wise with the another matrix, that's it. So I hope you understand. So in this matrix addition, we have a properties over there. So we have some kind of properties. Like we have a commutative property. So what do you mean by a commutative property? So like if we have a plus b, it is must be equal to b plus a. I hope you're getting. Means like LHS is equal to RHS. It's just a kind of thing. But if we add two numbers, it must be equal to B plus A also. Means opposite also. Like for example, I will give you like 2 plus 3 is equal to 3 plus 2. Yes. 2 plus 3 is equal to 5 is equal to 5. So this is called as a commutative property. And then we have a associative property. So what do you mean by associative property? It's just having a bracket out there. So like we have example, like just see like A plus B plus C over here, and just we simply the bracket comes here. It's nothing matters. Like we are not multiplying over here. Just we have like a kind of set over there. So like if we have an example like 2 plus 3, and that is equal to this one also. It's just the answer is equal to 6 is equal to 6. The answer is same. Means it following the associative property. But some of the matrices doesn't follow the associative property or the cumulative property. So we're going to get those in just few minutes, I think so. Yes. So after that, the dimension should be same. Otherwise it is undefined. So like the dimensions we are adding two matrices, like so we are adding two matrices. So the dimensions must be same, bro. So if the dimension not same, then how we can add? Like it's just undefined. As I told in our vector lectures, like if we adding like 2 3 2 3 5, we are do these two, but we don't have any kind of thing over here, so it just become undefined. So same as here also. So if the dimensions didn't match, and then it will become undefined. Okay, so like as a matrix have a m into n, and the B matrix has also m into n. Means the dimension should match, otherwise it is undefined. And I have said like a matrix addition, just try out with the subtraction. You will get it. You don't worry. It's just a small thing. Like here we add, and there we just subtract. That's it. I hope you do it. So and then we have something special as matrix multiplication. So it's just a kind of thing like matrix multiplication. So we just multiply two matrices. That's it. Here we just multiply two matrices here. So the some difference here, like we don't do the element wise here. So like as we are doing like this. So we don't do element wise. So like we have a something. I'll give you a good example. As I come, the first row of the matrix A is multiplied with the first column of the matrix B. So I just highlighted in a blue color like this. So these two are added. These two, not like as I have a this. I hope you getting it. Like, so we are not adding the element wise. Element wise we are taking the first row and we are taking the first column, and just we simply multiply them. I hope you get it. Like, just we add it, just we add it. So for example, as a given, like we have a matrix and we have a b matrix, and just we simply, if you multiply them, then the one is multiplied with the 5 and the 2 is multiplied with the 7. So it done. So after that, the 1 is multiplied with the 6 and the 2 is multiplied with the 8. I hope you're getting. Like, so the 3 is multiplied with the 5 and the 4 is multiplied with the 7. Yes. And the 3 is multiplied with the 6 and the 4 is multiplied with the 8. So after we just multiply like 1 into 5 and 2 into 7, we're going to get, after we do the multiplication, we just get our resulting matrices. That's it, bro. That's it. It's just simple. But we don't do we don't do the element wise. It's just a kind of new thing. But having a rows and the columns, we just multiply these two. Otherwise, it's going to be like a, as I said now here. So the scalar and the matrix products, like we do, it will become like this. But it's just a matrix and the matrix multiplication. We have two matrices here, just a thing over here, and that we have a summation formula over there. Like, if 1 is equal to from 1 to n, and we have a ai bi, means a matrices and b matrices. It's just a formula over there, or you can remember or just leave it. It is not that much important. It's just a formula, that's it. I hope you understand. And we have a properties. So we have a properties out there. So the cumulative property is not applied here. So like, a into b is not equal to b into a. So for example, just look at this. So 1 into 2 is 5 into 7. So just take this, and just, if these change, if these change, like if the 5 become here and the 1 2 become there, so we're going to get this first point. But here, if the 5 comes over here, if the 5 comes here, and then the 5 into 6, then the 5 into 6 will become here, and if the 7 comes here, and the 7 into 8. So here the value is changing. Are you understanding? Like, here the value is changing. So here the cumulative property does not apply. So it is not equal to LHS is equal to RHS. So I just, the rows and columns, if those change, and then it's not equal to. Yes. So after that, we have associative property. So associative property is like, so as simple as I just mentioned in the matrix addition, it's just as, but we use here the multiplication. That's it. So for example, if 2 into 3 into 3 is equal to 2 into 3 into 3, so the both answer is equal to, they both are answers are equal. The both answers are equal, and we have a associative property over here. So we have something known as a distributive property. So what do you mean by a distributive property? Just as I said, like we have a addition over there. That's it, bro. Like we multiply a, we multiply a, and then we simply adding the inner matrices, like, and it will become element wise multiplication here. So if I will give you some example, like 2 into 1 plus 2, then that is equal to 2 plus 4. If the answer is 6, and if we have same like 1 plus 2, and the answer will become 3, and 2 into 3 is equal to 6. Here also 6. So they both are equal. So I hope you get it. So here the row of the first matrix and the column of the second matrix. So how we multiply? So if we have a matrix over there, and we have another matrices over here, we have a two matrices, and we're going to multiply. So we're going to multiply these two. So here it is 2 into 2, but here it is 2 into 3. So like the dimensions didn't match. So you might think like it is undefined. But it is not. Like the second row means the columns should match with the rows here. The columns should match with the rows. Or you might think like the rows of the first vector should match with the columns of the second vector. The rows of the first matrices should match with the columns of the second matrices, and the resulting matrices become the resulting matrices will become 2 into 3. Yes, the resulting matrices will become like 2 into 3. It will become like this, 2 into 3, as here. So, and then we have something known as matrix vector product. We have seen like addition kind of stuff, but we didn't see the multiplication. It's just similar to the matrix multiplication. Here they have both matrices, but here we have a vector and a matrices. That's it, bro. So here we have a something strange formula, but it is nothing else. Like we have a matrix and a x vector, and we are simply multiplying with the each one. If the x1 is 2 and the x2 is 3 and the x3 is 2, another 2, it's just a simple kind of problem, just a simple kind of formula. That's it. There is nothing over here. So you are seeing this formula and what the heck is this, but it's just a simple formula as the process over here. So I'll give you some example. Like a is equal to, we have a matrices over here. So we have matrices and a vector we have taken a vector also. So is this possible? Like we can multiply with the matrices with the vector? Is this possible? So like the dimension didn't match over here. So as you clearly understand, as I previously said, the rows of this and the columns of this should match. Is this matched over here? Is this match? No, right? So it is undefined. If we multiply this and then it is undefined. So what we have to do? So it is undefined, and then we have a vector, and we have a vector 2 3 over here. We have a vector 2 3 over here. So here we have a, here we can multiply this. So we just multiply with our matrices. We just multiply with the matrices like element wise. Like we just multiply with these vector with the matrices, and we'll get there is a process as like this. There is a process as like this, means like adding these two and then getting our output. And just try it out on your own. And then you definitely get it. Or if you don't get it, just Google it. Or it's just a kind of simple thing. I hope you do that. That's it. And the resulting always vector in a vector multiplication. Like if we do vector multiplication, the resulting answer, the resulting output is always a vector. That's it, bro. That's it. We have covered something known as, so first we have covered what is matrices, and we have something known as, we covered how they are useful, and we covered the scalar vector, the scalar matrices multiplication, and we have a matrices addition, and then we have a matrices multiplication, and then we have some kind of properties over there, and we have a matrix vector product. So after that we're going to cover the transpose of matrices. So what do you mean by transpose? As I said in our previous lectures, like it just flips his body from one to the another end. So it's just similar to the vector transpose, but a little bit different. So what is a little bit different, we're going to see. So it just flips his diagonal. In vector we don't have any diagonals, right? So here we have a diagonal over here. So just flip its diagonal and make it reverse. So reflects A over its means diagonal to obtain a transpose. So if I will give you example. Like A, we have a matrices over here. If we apply the A transpose here, it just flips. So remember, just forget these two. It just flips. The three will here, the 3 will come here, and the 2 will go down there. So the answer will become like this. So forget this diagonal, the diagonal remains same, but it just flips over here and then flips, that's it. It just flips his diagonal, flips its diagonal. So I hope you getting it. So the transpose is just a mathematical a kind of formula, like the transpose of aij. So you might think, what is aij? It's just a kind of new thing, right? Aij. So nothing there, bro. Like aij means ith row and jth column. So if I is 1 and j is 1, and the row the first one is 1 and the column 1 is 1, so the answer is 1. So here we calculate row and we have calculate the column, and when these two matches are there, and just we simply plot that, and we'll get the, when we will give the aij number, that's it. So here the rows will become columns and the columns will become rows, as I said, in a similar to the vectors. So here is a example, a better example. We have seen the 2 into 2 matrices, but we didn't see the 3 into 3 matrices, right? So as I said, it just flips its diagonal, that's it. There is nothing special out there. So the 5 6 9 is a diagonal, so the same, it remains same, and just these values are changing, it's just coming down here and just going up there, and just coming down here and just going up there. So the diagonal is same, but it just flips. I hope you understand it. Like the B transpose is just transposing its form, it's transposing its body, from this to, from our head to tail to head. So it's just giving a kind of example like this. And we have some kind of properties out there. So we have a plus b transpose is equal to a transpose plus b transpose. So you're going to get, just explore it at your own, just explore it by own. It's just a simple thing, like 2 plus 3, we have a transpose over there, it will become 2 transpose plus 3 transpose. So we can't make the vector like here, so we can't make the matrices here. Just I am giving a sample example right here. So we have a plus b whole transpose become like a transpose into b transpose, and we have a c constant over there, and the constant we bring out the constant over there, and we have a transpose is here, and the determinant of a transpose is equal to determinant of a. So we going to know the what is the determinant in just a few, maybe in a next lecture, I hope so. So yes, it is planned, bro, it is planned here only. So it is planned here, so you don't worry, you will get it, and then after that we have a transpose inverse is equal to a inverse transpose. I hope you understand this, and we're going to cover in our next lectures. So we're going to cover some of the most interesting topics in our in our further lectures. So until then, bye bye. Just recapitulate what I have said, and just be fresh in the next lecture. So I hope you do that. So until then, bye bye.